Invert binary tree. Given the root of a binary tree, invert the tree and return its root. Yeah, so this algorithm is going to be pretty simple. Whenever you deal with trees, it's a pretty good idea to think recursion. That's usually going to be the case, especially with binary trees, but really trees in general. Um, yeah, trees and recursion go together quite nicely. So what is inversion? It looks like the if this inverts to this, the root doesn't change, and it looks like the left and right children swap. And you'd want to do that all the way down. So since it's a tree, you could say like call invert tree on this. That would be the top level one, and then you'd call it on each of the children. So then you'd call invert tree on this child and on this child, and then on this one, you call it however far down. You got to define some stopping criteria. So with recursion, obviously you need a base case. You don't recurse forever. An obvious one would be if the root is null, you don't want to recurse on it. So I'll go ahead and start with that. So if not root, return. Now this is always obviously going to return null because you're checking with it if it is. The other condition I'm going to add is I'm going to go ahead and not recurse if both children are null. And do I actually need to? I'll think about that. I'm gonna continue, and I'll come back to that base case and decide if I want to stop in that instance as well. So we're gonna need to do the swap. So we're gonna need a temporary variable to do it. If you have messed around with reversing a linked list, or anytime you want to swap two variables, you generally need a third one to hold one of them temporarily. So it's gonna be tree node temp, and that's gonna equal to root. I could be either child, so left or right. And we know that root is not null because of this check. And then root left equals root right. And then the right is the temp. And then we need to recurse on both children. So invert. We don't actually need to check the output on the sub recursions. It just has it. I'm honestly not even sure why it has us return the root, because it could just keep track of the original one and see if it comes out right. There's whatever. That's just part of the function signature it requires. Invert tree root right, and then return. Let's see. So we're not going to hit errors here because this is not null. Do I care? Okay. If both children are null, we'd still swap them. And then both of those would, so when we recurse on the null children, that would exit out. So this is correct. I guess you could add another condition where if both children are null, you don't recurse. But I think this will also work just fine. It'll do a little bit of a extra effort on the null children, but that would be constant. So let's talk about time and space. This it's basically depth first search. It's recursive, and it's going to recurse once on each of the nodes, and it's a tree. So it's going to be O of V, magnitude of V. So V is the set of vertices, and the magnitude bars means the size of the set of vertices. And since it's a tree, we know that the number of edges is less than the number of vertices, actually. I think it's usually one less than. So let's see if there's 1, 2, 3, 4, 5, 6, 7. If there's 7 nodes, 1, 2, 3, 4, 5, 6. 7 nodes, 6 edges. So yeah, always one less edge than the number of nodes. So for example, writing this part where E is the set of edges and the bars means the size of the set of edges. This cancels out. Actually they're always like of the same magnitude, so you could erase either one. That would be correct. Since V is technically a little bigger, I'm going to go with that. So this is both our uh, time and space complexity. The reason for that being, let's see, what do we do for each of these nodes? We do this. This is a check. That's constant. This is constant assignment, and we do these recursive calls. And we're going to end up recursing on each node once, including these null children at the bottom. And there's also the tree could be very unbalanced. Keep that in mind. I think it'll still work just fine. And as far as space complexity, well, suppose it is very, very unbalanced and the entire tree is just like, say, down the left child, say it's just a line. Well, you'd end up with a stack frame for each child in memory at the same time. So it is going to be, linear time and space. And then that's pretty much it. I think let's go ahead and give it a run for syntax. Let's see. And like always, anytime you do anything recursive, you could also do it iteratively, so you're not doing a recursive call. I think recursive is usually the better way to go in interviews. One, because like people get weirdly, uh, people get weird about it. Like for some reason they like it. Interviewers like it. I guess just because it makes them feel like they're doing Inception or something. But realistically, machines have a limited number of stack frames, usually I think in the tens of thousands, as opposed to if you did it iteratively, then you would not have that kind of constraint. You could go much, much, much. It would scale better realistically in terms of space in a way that's not as easy to capture by these theoretical time and space analyses. Just the fact is computers hard code a limited number of stacks as part of the operating system. And but that being said, in an interview setting, besides whether whatever's good or bad, it's faster to write. It takes fewer lines of code, and when time is of the essence, you want to minimize lines of code and the amount of clarity first and foremost. But if you can make it simple and short, that's the way to go. So I'm going to go ahead and run it. I think I've said everything I can say. Cool. And then submit. All right. And thanks.